All right, MEGN 200, welcome back to another online Arduino activity. This time we're going to be talking about electrical power. So electrical power is given in units of watts, which is a joule per second, right? It's the amount of energy that a device is consuming in a given period of time, right? So this is a very important concept for powering motors, heaters, any sort of device that's going to use a fair amount of electrical power. We need to take that into account when we're designing circuits. We need to be able to size wires and devices so that they can supply enough power to actually accomplish what we would like to do in our engineering system. So the way we can calculate power for an electrical device is with this very simple equation, P equals IV. All right, so P equals IV tells us that the power is the current flowing through that device times the voltage drop across that device. So current's given in amps, volts given in volts, right? If we multiply those together, we'll get watts as our output unit. You can also substitute in Ohm's law into this equation for V, and you can obtain an alternate form, which is P equals I squared R. That's useful if you happen to know the resistance of your electrical device that's doing work. So we'll take a look at this equation, how we apply it, and then we'll use this equation to measure the amount of power that's consumed by the little motor in your guys' kits. So one of the things you'd notice on the previous page there was that I shows up in both of those equations. So we need to know how much current is flowing through our device that's actually doing work. So what I have here is just a generic system that we would use to sense how much work is being done by an electrical device. The electrical device here is represented with this resistor. It's called RL, which just stands for load. So it's just any sort of electrical device that's going to consume power. We just call that a load. We also have our voltage supply, which is supplying voltage into the circuit. And then we have this resistor up here, which is where we're actually going to be using to make our measurement of how much current is flowing through this circuit. We call this one RS, that stands for Shunt Resistor. So the Shunt Resistor is a resistor with a relatively small resistance value. We don't want to add a bunch of extra resistance into this circuit that might affect how the load performs. We just want to measure the load, not change how it's performing. So what we can do here is if we know the resistance value of RS, we can measure the voltage drop across RS and then calculate how much current must be flowing through RS. Because this is a series circuit, there's nowhere else for the electrons to go out of this circuit. They have to go around this series circuit, so the current has to pass through RS and then through RL. So if we know the current going through RS, we know the current going through RL, so we know I, and then we just need to know what's the voltage drop across RL to be able to calculate the power that's being dissipated by RL. So what we'll be doing is we'll measure the voltage at this point and at this point to get the voltage drop across there. And let's take a look at a more specific system here. So if we measure the voltage drop across this 10 ohm resistors, this is the circuit you guys will actually be building to measure the power consumed by your motor. If we measure that, then we know the current flowing through this resistor, and we can also get the voltage drop across the motor. So this is the motor in our circuit here. So we're measuring V2, and we know that this terminal on the motor is just connected directly back to ground, or the negative terminal on our power supply. So this whole branch of the circuit down here between the motor and the power supply, there's no resistors or anything in there. That's all going to be 0 volts. So if we know what V2 is up here, then we know the drop across the motor because it's 0 volts down here. Okay, so that's how we're going to be actually calculating the power of our load. So I have my example set up here. This is the one you guys will be building. So we've got our motor. Motor is connected to a 10 ohm resistor, which is connected to the positive voltage supply. I'm using the breadboard power supply today. You could use the 5-volt pin on the Arduino if you can't get this to work or you don't have a good battery or a power jack that I've got plugged in here. I've tested it both ways. It does work with the 5-volt pin. And I am measuring V in, so that'd be V1 at this point here with this white wire that's going to an analog input. And then V2 is being measured with this sort of peach colored wire that goes into another analog input. So I've got my two voltages. I know that this is a 10 ohm resistor, so I can calculate the current, and I'll know the voltage drop across my motor. So then I can use P equals IV to calculate how many watts this motor is using as it spins. So let's go ahead and we'll pull up the serial plotter where I have the Arduino spitting out the power value in milliwatts, and we can graph that power as the motor runs. So let's bring that up. All right, there we go. And we'll just shift a little bit so you guys can continue to see the setup here. All right. So right now, everything's turned off, and you'll see the serial plotter is reading that we're consuming 0 milliwatts. So if I turn this off, we should see a big spike, and the power should come up rather rapidly. It does. Okay, and you'll notice it's quite noisy. You'll see that line's jumping around a lot. That's a real thing. So this is a brushed DC motor, which means it has little connections inside of it that are constantly disconnecting and reconnecting. It's doing that so it keeps a magnetic field spinning in one direction so that the motor will continuously spin in one direction. What that means is that the power is actually being turned on and off really fast, and we're able to see that with the Arduino, which is pretty cool. So right now we're sitting at about 300 milliwatts or so being consumed by this motor. So let's see what happens if I start to load the motor up. So I'm going to put my finger on the shaft here to force the motor to work a little bit harder. And notice the power climbs way up. Then I can release it, and the power will drop back down to sort of its steady state. One of the other cool things that we can do is you can turn this power off, and you'll see the power drops rapidly down to 0. But watch it again when I do this. Right when I turn it off, you notice that the power goes negative for just a split second. So what you're seeing there is actually what we call back EMF or flyback voltage. You'll learn more about this in the transistor activity, but this is an effect that happens when you turn off something like a motor that's got a large inductance to it, as it tends to send current backwards through your circuit. All right, another cool thing that you can see with this demo is when I turn the motor on, you see we get a big spike in power. So it takes more power for this motor to get up to speed than it does to maintain its speed. And you can see that with this relatively simple setup here, which is pretty cool. All right, so that is the demo for today. So this is really a pretty cool setup because you can measure the power of a small electrical load with just the items in your kit. This ends up being important because if you start to get to bigger motors, we'll start to need to think more about our supply. So hopefully what you realize from P equals IV is that you can't just pick a voltage supply based off its voltage alone. You need to consider how much power that voltage supply needs to deliver to the load, which means how much current it can also supply. If we have a big starter motor in a car that runs off 12 volts, it's not going to run off of just a small benchtop 12 volt power supply because it's a big high power motor. It needs a ton of amps at 12 volts to be able to turn itself over. So we need to consider how many amps our load is going to take before we pick out a power supply. So something to keep in mind as you work on this activity. As always, if you run into any trouble, drop into class or office hours and we'll be happy to help you get your power measurement up and running. Thanks again.